Well, thanks for joining me. I'm Dr. Ryan Hayes at Andrews University Department of Chemistry and Biochemistry, and we're going to spend a little time talking about spontaneous electrochemistry that's all around us. Yeah, those are big words, right? But I'm just talking about corrosion and batteries. So we're going to just take a quick look here today at some of these applications of spontaneity that's all around us. Many of us are familiar with rust, especially if you've grown up in the Midwest. In Michigan, we call it the Michigan cancer. Ugh, rust, what is it? It's iron oxide. Rust is the oxidation of iron and other metals that occurs, especially in wintertime with the salt, the water, the rain. Oh, it's terrible. It's hard to fight it. And when I was younger in the 1980s, there was cars rusting all the time. It was bad, but it's gotten a lot better. How would they fix that? Here's the problem with rust. It's brittle, it falls apart, and it just crumbles in your hand. There's no strength to it. Secondly, doesn't conduct electricity. So I've come across that a number of times, been able just to wipe off with a scrubby or sandpaper and get the rust off of some electrical connections after you turn the electricity off. And you can get things to work again that you thought were broken. Sometimes you just got to take a few things apart, clean off the connections, boom, it's working again. Why? Rust. Oxidized materials do not conduct electricity. Two big problems with rust and oxidation. So how does that happen? Spontaneous. It's spontaneous. It just happens. How? Well, corrosion is a process of metals returning back really to their original form of oxidized. We live in an oxidized atmosphere, and the oxygen in the air is just going to react with these metals in a spontaneous way because of their electrochemical potentials. So they're going to go back to these oxidized ways. That's the way we find them. In fact, the next part of our chapter is about how do you take these oxidized materials and get the pure metals out? More good electrochemistry. So the oxidation that takes place is the addition of oxygen to these pure metals to create the oxide. The most common example is then the rust, is what we call it, as iron oxide. And that process has a huge free energy and a very large equilibrium constant. It's going to happen. Rust is going to happen. How do you fight it, though? How do you fight it? We're going to find out in just a second. Just as a reminder, oxides, they're salts, iron oxides. They're brittle. They don't conduct electricity, and that's not good. This is how I remember Toyotas. Don't see that too often. They must have figured out how to fight corrosion. So what is corrosion? It is kind of like a concentration cell, it feels like. You can get an spontaneous electrochemical reaction that occurs between iron and typically oxygen and water, and if you have some salts around here, that will help. And so there's a part of the metal that will act as an anode, another part it will act as a cathode, and that spontaneity right there that takes place will transfer electrons and start to make it real easy for iron ions to be made. Iron ions can then make iron hydroxide, and eventually that leads to iron oxide. Rust. Terrible. Spontaneous electrochemical reaction between iron and oxygen. Notice that you need water around there, and if you have salts, those help conduct electricity. What about aluminum? We've got pure aluminum in most people's houses. You've got aluminum things. That doesn't seem to rust. Does it rust? Yeah, it actually does rust. Interestingly enough, aluminum rusts pretty quickly, but it forms a very thin, transparent aluminum oxide coating that's very flexible, that bends with the material. It's so thin you can't even see it, but it's there. And this aluminum oxide is quite tough. And once that forms, that strong aluminum oxide layer protects the rest of the aluminum. So just having a thin layer of rusted aluminum actually is what protects it. And in fact, ruby is one of the strongest materials that we know, is primarily composed of aluminum oxide. It's very hard. It's very corrosion resistant because it's already corroded, aluminum oxide. In fact, anodized aluminum, which is just aluminum that's been undergone some electrochemical treatment to make it really a thicker layer of aluminum oxide on it, that is used to actually transport nitric acid. I've done a lot of fun experiments with aluminum and acids, and they react. They react and it makes hydrogen gas. Nice redox chemistry right there. So I find it very strange that we use aluminum tankers to haul acid around it, specifically nitric acid. And the reason is nitric acid, for some reason, doesn't eat through the aluminum oxide. So if you anodize it and make a nice thick layer, nitric acid can get through it. But nitric acid will just react with any other type of metal. So how do you protect it? Well, if it doesn't form this nice little layer like aluminum does, you can put a sacrificial metal in electrical connection to it somewhere. So this is what's happened to iron pipes. They would stick, connect to wire that's insulated, which means it has like plastic or something around it, and put a big magnesium chunk connected to it. Magnesium, as we know from our electrochemical reduction and tables, will oxidize more readily than iron will. So if you put another metal that oxidizes more readily, how do we know that? Because the oxidation potential is much higher with magnesium. The electrons that are going to go in the electrochemical reaction will actually go to the magnesium, and magnesium will start rusting first before the iron. So that's actually quite valuable. So by putting something, another metal nearby in electrical connection with it, or mixing it in, that metal will react, the other metal will react first before the iron. So all these metals work better at oxidizing than iron. And many of them are low, cost less, and for the most part are safer. Ooh, like magnesium, aluminum, zinc, chromium, nickel, manganese, there's others, lithium, potassium. Some of those metals are very reactive, so you don't want to have them around. They're just so reactive, they're gonna rust right away. And so magnesium does a pretty good job of rusting, but not too much. So magnesium rods are often like in water softeners, and next connected to water pipes. So that's magnesium is often used there. Another way is just to coat it with a whole nother material like zinc. A lot of nails are galvanized, coated with zinc. The zinc then will oxidize and rust and fall off way before the iron will. So this allows nails to last a lot longer. Or you could make a new alloy with these materials in it, like chromium, nickel, and molybdenum. These are alloyed into steel to make various types of stainless steel. So steel is just iron, but it's an alloy with these different sacrificial electrodes materials in them. So these are a number of ways then to fight corrosion. Put in a sacrificial metal, put it in mix it right in, alloy it in, put it in electrical connection with it, or coat it. So that's corrosion kind of in a nutshell. Let's talk about batteries for the next few minutes. Batteries are another spontaneous voltaic galvanic cells that we can use to generate electricity. And a very common one is using zinc and for the anode, and using manganese oxide with some ammonia in as the cathode. This was originally done under acid conditions, but they didn't last very long, so they had poor shelf life. Later, as they ran it in more alkaline conditions, these batteries lasted longer, and thus we have our alkaline batteries. So this is the general chemical reactions for alkaline batteries. So it's called a primary battery, because you basically, once the metals are used up, you can't really recharge that. Or can you? Some people have tried. It doesn't work very good. I've tried as well. The second type of batteries, a secondary battery, is one that you can recharge. This is a good example of a rechargeable battery is the lead storage batteries that's used in cars or small vehicles, go-karts and lawnmowers, and these sort of things. They use a lead storage battery. It's very heavy. Lead is very dense. These can be restored by applying a charge, which is what an alternator does, or some kind of voltage. You can use another battery, a trickle charger, and you can recharge batteries. You can't do this indefinitely because of the reactions that will occur. One of them here in the lead storage battery, it's using lead. I'm going to show you the chemical reactions here next. Lead oxide ends up forming and falling off because of that brittle nature, and it doesn't go back in the way that it should. So here's the chemical reactions associated with the lead storage battery. Lead react with hydrogen sulfate. Will make lead sulfate with a 0.36 volts. That's at the anode. The cathode reaction is lead oxide. As long as it's sticking to the electrode plates there, it can react to form 1.68 volts for the reduction potential. Put those together, you get about 2 volts. Using some electrical knowledge, you can put them in series, and that will add the voltages together. If you put 6 of them together, you can get a 12-volt storage battery, and that's a very common type in our cars. 12 volts, they have 6 of these plates in there of lead and lead oxide. And the sulfate, hydrogen sulfate, comes from sulfuric acid, and sometimes you have to recharge these by putting in more sulfuric acid. We'll let the companies do that. You don't have to do that on your own. Another very common secondary battery is the lithium battery. Many of these actually probably falls in both primary and secondary types. Since lithium is such a high oxidation potential at 3 volts, you're already on a head start with generating a lot of voltage here. So there is a ton of different types of lithium batteries out there. These little watch batteries, those are all lithium. The most common one uses metallic lithium as an anode, which is kind of flammable, and magnesium dioxide is the cathode. And they'll have some salts in there to help get the electricity to flow. If you want to learn more about a number of them that are out there, you can look at Wikipedia. It has a nice article on lithium batteries, a lot of different types. They have some issues with them. The new ones, people are trying to just come up with better ones that last longer, recharge faster, and one option is potentially using air as one of the electrodes. So a lot of interesting applications there for lithium batteries that are all around us, in our phones, watches. It's a great material for that. Another interesting battery is the hydrogen air fuel cell. Now, if you think fuel, it sounds like I need to put fuel in it. That doesn't sound like a battery. Trust me, it's a battery. And the reason why they call it a fuel cell is that the materials that get used up, the anode and cathode materials, are actually fuels. There's many different types of fuels you can put in there, but ideally, if you can use hydrogen and oxygen, these will come in on the anode and cathode side, and if they're separated by a special membrane, usually a special proton transferring membrane. Nafion was one that the company I worked for used to use. You can put this in there. You gotta have really clean oxygen, really clean hydrogen, otherwise it'll mess up the proton exchange membrane. And you can generate 1.23 volts using hydrogen. That's part of the standard hydrogen electrode. And then the reduction potential of oxygen there can create 1.23 volts. 1.23 volts. And if you put a number of these in series, you can generate 6, 10, 12 volts or more. And how do you recharge them? Well, these things can keep going if you just keep putting in good hydrogen and good oxygen in there. And some have been developed using oxygen from the air and hydrogen that comes in some kind of canister. Now, typically, and this has proved to be sort of the best way that car manufacturers have used, it's just some kind of carbon reinforced high pressure canister. So you just have a high pressure hydrogen storage tank on your car. And that seems a bit scary, but that seems to be the way to do it. And there's actually some manufacturers out there like Toyota who have made some fuel cell vehicles. So instead of having the charge overnight, you can just inject some more fuel in there, load it up, pressurize it with hydrogen, and you're good to go for maybe a couple 100 miles. So very interesting technology. So you don't recharge it with electricity, you recharge it with fuel, hydrogen that is. Scientists are looking at ways to store hydrogen not as a pressurized container, but maybe have it trapped inside of a metal alloy, and then that gets released as it's needed. So that doesn't seem to be the way that is working out so far. They just put it in a pressurized tank. I actually used to work for a company called Lintec that made fuel cell testing stations, and then some of the people that I worked with end up making a fuel cell generator. and you would just load this, I think, with methanol or something that they would use as the fuel source to generate hydrogen, oxygen from the air. And it's a generator, generates electricity. And they actually showed it working at a tailgating party to run a TV and satellite dish and some other things. Pretty expensive, thousands, $5,000, $10,000 or something, but it makes no noise. If you've ever come across a generator that's based on a little engine, those things are loud. I think it's a battery. It's a big battery. And you recharge it by putting in more fuel. I think methanol, as I was saying. Is it possible to have a battery that could last 20 years? Yes, that someone's actually come up with a battery that actually uses nuclear chemistry. And that's going to be our next topic in our class, is looking at, the next chapter is at nuclear energy and nuclear materials and reactions. But someone has tapped into that to create a 20 lifetime battery. So I'm not going to go into the details, just want to talk about City Labs. You can go look at their website, and because sometimes you need like sensors. It's not a very big battery, but sometimes you don't need a big battery, and you want a sensor or some kind of device that's out there collecting information that just needs a little bit of energy for a long period of time. That may be out there. So what should a student know from this? You should know what corrosion is. You should know how it's formed, and then how to block it. What are some blocking technologies out there? What are some common batteries, and what is a fuel cell? So if you get a chance, go watch there's some great videos on YouTube on all of these things, but we should start to learn more about the world around us. There's all these spontaneous electrochemical reactions that are occurring, and hopefully you know a little bit more now and how we use them in our society. All right, thanks for joining me. I'm Dr. Ryan Hayes, and I hope you have a great day learning more about the chemistry and the world around us.